Let's take a look at our example from the human migration patterns in Flagstaff or in Coconino County. Remember that we had 5% of people in the urban environment at time n transition to the rural environment at time n plus 1. 85% of the people in the rural environment at time n stayed in the rural environment at time n plus 1. And 15% of the rural people at time n became urban people at time n plus 1, and 95% of the urban people at time n became urban at time n plus 1, or remained urban. So 95% of the people stayed. And then we were able to write it like this as the direct equation, where we just took a to the t times our initial state. And what we want to do here is to show, we already showed mathematically by computing the steady state vector what happens in the long run, but now we want to see, using the diagonalization vector decomposition theorem, we're going to write equations for r sub t and u sub t as functions of time, then explain why it makes sense that after repeated multiplications by a, that is, years passing, the transformed vector approaches the steady state ru equals 25/75. So first of all, we need to compute the eigenvectors and eigenvalues of that matrix. So here they are. And now what we're going to do is, again, start off by writing our initial state as some multiple of v1 plus some multiple of v2. So we're going to solve for k1 and k2. Now our x naught vector, that was our initial state in this problem, which, remember, we had 20 rural people and we had 80 urban people at time 0. So now we have k1 times v1, which is the 1/3 1 vector, plus k2 v2, which is the -1 1 vector. And now we need to solve for k1 and k2. So that means we have a system of equations. Coefficients of k1 are 1/3 and 1. Coefficients of v2 or k2 are -1 and 1. And then we want to achieve the constants 20 and 80. So again, our k1 column, our k2 column, and performing Gaussian elimination on this using technology, we would get, we would get 1, 0, 75, and 0, 1, 5. So this tells me that k1 is 75 and k2 is 5. And again, we're just going to check to make sure this works out, so we believe it. So that means that if I take k1, which is 75, times v1, which is 1/3 1, and I take k2, which is 5, times the -1 1 vector, and I add these together, 75 times 1/3 is 25, 75 times 1 is 75, plus 5 times -1 is -5, and 5 down here. And now when we add these together, we see that 25 minus 5 is 20, 75 plus 5 is 80. So we have effectively solved for k1 and k2. So next, just like in the previous problem, what we're going to do is we are going to decompose this into the diagonalization vector decomposition theorem. And that says that x sub t, the two states at time t, are going to be k1 lambda 1 to the t times v1. And since this is a 2x2 matrix, it's only going to have two terms. In our next lesson, we'll actually look at multiple states where we can, we'll have a third term in it. And that would be the same process, just larger matrices to deal with. And so now I'm just going to plug in what I know. So I know that xt contains my two states, r at time t and the number of people in the urban environment at time t. k1 is 75, lambda 1 is 1. So we have 1 to the t power. v1 is the 1/3 1 vector, plus k2, lambda 2 to the t. Now lambda 2 is 4/5, which we'll write as 0.8. 0.8 to the t power times v2, and v2 is negative 1, 1. So already one of the things to notice is that as t approaches infinity, if you take a decimal to a really large power, this guy here is going to approach 0 as t approaches infinity. This doesn't always happen, it just is the case here that one of our eigenvalues is a fraction, and when you raise a fraction to a large enough power, it's going to approach 0 for large enough t's. So at that point, we're going to see that what we're left with is, well, 1 to the t is 1. You can exponentiate 1 to whatever power you want. 1 to the 100th is still 1 times 1 times 1 times 1, dot, dot, dot. So this will just be 75 times a third, which is 25, and 75 times 1, which is 75. So we see that we're going to end up getting, in the long run, the state 25, 75. But let's write this out in scalar form. So r sub t is equal to 75, 1 to the t times 1/3. Again, 1 to the t is just equal to 1 for all t. And so we'll have 75 times the 1/3 vector, which is just 25. And so for u sub t down here, let me write this in vector form, 75 times 1 to the t times 1 is just 75. And then I'm going to add to that k2 times 0.8 to the t times negative 1. So my k2, I forgot to write it in here. Here, my k2 was actually 5. And so we'll have 5 times 0.8 to the t times negative 1, which is minus 5 times 0.8 to the t. And 5 times 0.8 to the t times 1 is just plus 5 times 0.8 to the t. So now you can see what's happening here. As you raise for large enough t, this term will decay to 0. This term will go to 0. This term will go to 0, again, as t approaches infinity, and all I'm going to be left with is the constants 25 and 75. So let's go ahead and actually model this in Desmos to see what this looks like. So I'm going to go ahead and just say this is r sub t at time x, we have to use x here unfortunately, equals 25 minus 5 times 0.8 to the x power, and u sub t of x is equal to 75 plus 5 times 0.8 to the x power. And let's just go ahead and zoom in on this on a scale. We'll just say we'll go from time 0 to time 20. And here we'll go from y equals 0 to y equals, we'll say 100. So here we go. So we can see that the number of rural people starts off at 20 at time 0. At time 0, u sub t starts off at 80. But we can see that over time, u sub t drops by a little bit, and it starts to stabilize out by about time 14 or 15. R sub t rises from 20 and then stabilizes out after about, again, time 14 or 15. And let me just put in a couple of asymptotes here. Y equals 25. You can see y equals 75. That these asymptotes are actually going to be the values at which the rural population size stabilizes at and where the U population stabilizes at. And the important thing here is that we described that as t becomes larger and larger, that it's the dominant lambda becomes the multiplier. So once that vector rotates into its direction, which it's going to go in the direction of this v1, but it's only going to be scaled by 1 each time. And since 1 is the dominant eigenvalue, that means that basically any additional multiplications by a are really just going to scale it by 1, and that's why we reach the steady state. So we can argue that if your dominant lambda is a 1, that you are going to reach steady state, and only under those conditions can you reach a steady state. If this was a 2, then ultimately our initial state vector would transform into the eigenvector, but then it would be scaled by a factor of 2 each time, so the values inside of here would actually double in the long run and not approach a steady state like we have here. So here, once again, we just have, this is our urban population at time t, this is our rural population at time t, and then one other thing we should just note here is that our axis, our horizontal axis is time over here, even though we're using x in place of time, but unfortunately Decimals doesn't recognize working with t as a variable. And so we see that steady state is definitely achieved. So conclusion is that we see that as t approaches infinity, the first term, 75 times 1 to the t times 1/3 1, will be much larger than 5 times 0.8 to the t, negative 1, 1. And therefore, for very large t, x sub t is approximately 75 times 1 to the t times that v1 vector, which, because this is a 1 to the t power and that equals 1, these values just become 25 and 75. That is, the vector will point in the direction of 25, 75, and every 1 unit increase in t beyond that value will simply cause the vector to be scaled by 1 additional factor of 1, a steady state. So that's where we'll stop this lesson. In the next one, we'll start looking at some modeling and how we can predict what happens when there's not a steady state. And things get very interesting when you start dealing with stage matrices, where you can actually incorporate a birth-death cycle into that process. So more on that in the next lesson.